Hi everyone. In the previous session of the chapter Amines, I discussed about physical properties and some chemical properties like basic nature of amine and acylation reactions. In this session, I am going to continue with the chemical properties or chemical reactions of amines. The third one is carbylamine reaction. Carbylamine reaction. So carbylamine reaction, you need to consider either aliphatic primary amine or aromatic primary amine, and that has to be heated in the presence of chloroform and alcoholic or ethanolic potassium hydroxide. We get isocyanates or carbylamines, and the reaction is considered as carbylamine reaction. Let me write the reaction of that one. As I said, you need to consider primary amine, so RNH2. This may be aliphatic or aromatic. That reacts with the chloroform. The formula is CHCl3, chloroform, or I can consider it as trichloromethane. And when you consider one more, that is potassium hydroxide, alcoholic potassium hydroxide. Potassium hydroxide, crystalline solid it is, that has to be dissolved in the ethanol, so that we get alcoholic potassium hydroxide. And when all these three are heated, remember that after heating only the reaction proceeds, and here we get a compound, and I call it as isocyanates, RNC, CN minus cyanide, NC minus isocyanide it is. And apart from that, we get byproducts like we get KCl and we get H2O. So this is the in general reaction of carbylamine. And now if you consider here CHCl3, 3 Cl we have, and therefore I need to write 3 KCl over here, and the potassium is also 3, and here I am going to write 3, and this is primary amine, and this is chloroform. KOH stands for potassium hydroxide, we know, and this will be isocyanate. And isocyanate you can call it as a carbylamine also. So this is how, when primary amine on heating with the chloroform and alcoholic potassium hydroxide, we get isocyanates or carbylamines, and this reaction is called carbylamine reaction. And now we'll see some particular examples for that one. So now I am going to consider an aliphatic amine, that is CH3NH2. So this is methanamine. When this reacts with the chloroform, CHCl3, trichloromethane or chloroform, and when it reacts with the alcoholic potassium hydroxide, ALC stands for alcoholic. As we know, you need to heat these constituents, and what we get isocyanide of respective the alkyl group. So therefore what we are going to get here is CH3NC, methyl isocyanate. The name of this compound is methyl, since we have a methyl group here. So methyl isocyanide is the main compound, and of course we get some other byproducts also, KCl and H2O we are going to get. So this is how, if you consider methanamine after carbylamine reaction, we are going to end up with methyl isocyanate. Similarly, I consider one phenyl, C6H5NH2. This is aromatic amine, and aniline it is. And when this compound is heated in the presence of chloroform and in the presence of alcoholic potassium hydroxide, of course we need to heat, and this is a symbol you need to consider, and here phenyl group we considered, therefore here we are going to get C6H5NC. The previous one was methyl isocyanate, and this one is phenyl isocyanate. And we get potassium chloride, and we get water. So this is how you can consider the aliphatic amine and you can consider aromatic amine. When these are heated in presence of chloroform and alcoholic potassium hydroxide, we get the respective isocyanates, and that reaction is called carbylamine reaction. And we have a particular characteristic property of these isocyanates. Remember that isocyanates, you can call it as carbylamines, it has a characteristic property, and that property is it has foul smell. If you consider the odor of the isocyanates formed, it has a foul smell, very bad smell, this isocyanate or carbylamine you are going to get. But remember, this carbylamine test is only for primary amines. So primary amines gives the positive test for this carbylamine reaction, whereas if you consider secondary or tertiary amines, and carbylamine reaction is not for these secondary and tertiary amines. And you need to know the reason behind that, why only primary amines gives positive test for carbylamine reaction. As we know, in case of primary amines, only one hydrogen of ammonia is replaced by either alkyl or aryl. In case of secondary amine, we have two alkyl or aryl. In case of tertiary amines, we have three alkyl groups. So when you move from primary, secondary to tertiary, the steric hindrance increases, so that to approach the lone pair of electrons which are present on the nitrogen will be difficult in case of secondary and tertiary. Therefore, carbylamine reaction is not for secondary as well as tertiary amines. Only primary amines gives the positive test for what actually carbylamine reaction. So one point I can say here, so if I give you amine and if you want to identify whether the given amine is primary amine, and the best test for that is the carbylamine reaction, carbylamine test, and the characteristic property is the carbylamines which are formed or isocyanates which are formed that has a foul smell, and based on that we can consider the given amines is primary amine. Fourth reaction is reaction of amines with nitrous acid. The fourth one is with nitrous acid. How does amines are going to react? The formula for nitrous acid is HNO2. Right, you know, nitric acid HNO3, nitrous acid HNO2 here. Now we'll see how amines reacts with nitrous acid and what kind of compounds we are going to get. First I consider aliphatic amines and later I consider aromatic amines. So here I consider primary amine, that is RNH2. When it reacts with the nitrous acid, that is HNO2, and what kind of products I am going to get, let me write over here. But how actually HNO2 or nitrous acid is produced, you need to remember by taking sodium nitrite NaNO2 and hydrochloric acid HCl. By taking the mixture of sodium nitrite and hydrochloric acid, nitrous acid is produced. When that nitrous acid is going to be react with what actually the aliphatic primary amine, let us assume this is aliphatic primary amine that reacts with the nitrous acid. This is nitrous acid as we know. And the kind of product what we are going to get here is, let me write over here, we get R N2Cl, I will write a plus over here and a minus over Cl minus, and this is highly unstable in nature, therefore I just place in braces or brackets. And the name of this compound is aliphatic diazonium chloride. So this is highly unstable compound. So diazonium, azo stands for nitrogen, so N2 plus, this is the diazonium group. So R is aliphatic as I mentioned here because I considered primary aliphatic amine. So therefore this intermediate or highly unstable compound is aliphatic diazonium chloride. Since it is highly unstable, so when you consider the hydrolysis of this, and we are going to get what actually ROH, that is alcohol we are going to get, and apart from that a gas is going to be released, that is a nitrogen gas, and one more byproduct we get it as what actually HCl. This is how when primary aliphatic amines reacts with the nitrous acid, we get unstable compound aliphatic diazonium chloride. On hydrolysis we will get alcohol, so ROH. So this is nothing but alcohol, and the kind of gas released is N2, nitrogen gas. So now we'll see one particular example. So if I consider NCH3NH2, and that is methanamine, and as we know, this is a primary aliphatic amine. When it reacts with the nitrous acid, the formula is HNO2, and the product what we get, as we know, nitrous acid is produced by combination of sodium nitrate plus hydrochloric acid. We are going to get nitrous acid, and we get the unstable product, that is CH3N2Cl. we have plus and minus. Okay, as we know, for nitrogen we need to consider 3 bond pairs, one extra we have, therefore plus and minus, that is nothing but the salt, and this is unstable compound, and you can call it as the methyl diazonium chloride, aliphatic in general, methyl diazonium chloride. And when you consider the hydrolysis of this unstable compound, we get an alcohol of respective aliphatic compound, that will be CH3OH, and this compound is methanol, or you can call it as methyl alcohol also, and the gas released is nitrogen, and we have one more byproduct, what is that? HCl. So this is how the aliphatic primary amines reacts with what actually the nitrous acid. And remember, name the gas released when aliphatic primary amines reacts with the nitrous acid, and remember the gas released is a nitrogen. You just see here in the particular example also, in general also, I mentioned what actually the nitrogen gas is going to be released. And how actually nitrous acid is formed? By taking the mixture of NaNO2 and HCl, sodium nitrite and hydrochloric acid. By considering these two mixtures, nitrous acid is produced, and that nitrous acid is going to be react with the primary amine, and respective unstable diazonium salt we are going to get, and later respective alcohol we are going to get. So this is how when nitrous acid reacts with the aliphatic primary amines. So now I consider aromatic primary amine, and the best example for that is C6H5NH2, and that is nothing but aniline. So when aniline reacts with the nitrous acid, that is HNO2, as we know, nitrous acid is produced by taking the combination of sodium nitrate and hydrochloric acid. Here also we get a kind of a compound, and what is that compound? Let me write over here, C6H5N2Cl plus and minus I write here, and the name of this compound is benzene diazonium chloride. Benzene diazonium chloride, and in short you can call it as BDC also, benzene diazonium chloride. And if you, this is also diazonium chloride, and this is quite stable, because this reaction has to be considered in the temperature of 0 to 5 degrees Celsius, or you can say 273 to 278 Kelvin. You can write in terms of degree Celsius or Kelvin. So at low temperature this reaction is going to be carried out, and at low temperature BDC or benzene diazonium chloride is quite stable. And this reaction may be considered further for the next, you can consider some different reactions of this benzene diazonium chloride also. And the one more product or the byproduct what we are going to get here is, we are going to get what actually NaCl, and we are going to get 2H2O. So this is how, since it is stable, and we get benzene diazonium chloride only, and that is for what actually if you consider aromatic primary amine. So in general I can say aliphatic primary amine and aromatic primary amines reacts with the nitrous acid and you will get respective diazonium chlorides. Whereas in case of aliphatic, since it is highly unstable and after hydrolysis you are going to get the respective alcohols and benzene diazonium chloride, or you can say arene diazonium chloride, and that is quite stable. And using this table, once BDC is prepared, and after that different kinds of reactions can be carried out, and this is unstable and this is stable. In one simple sentence I can say why this is stable, because there is a resonance stabilized, and how it is resonance stabilized we are going to discuss later. Right now you remember the benzene diazonium chloride, that is quite stable, whereas the aliphatic diazonium chloride, that is unstable. That is the reaction of amines with nitrous acid. Now we'll see the reaction of amines with aryl sulfonyl chloride. Let me write over here. So this is a reaction of aryl sulfonyl chloride. So fifth one, it is reaction of amines with aryl sulfonyl chloride. Let me consider one particular compound. Let me write over here first. Benzene sulfonyl chloride, and the formula I can write here C6H5SO2Cl. See here, C6H5SO2Cl is nothing but benzene sulfonyl chloride. As we know, SO2Cl stands for sulfonyl chloride group. So this compound is nothing but, this is called Hinsberg's reagent. This is Hinsberg reagent. So Hinsberg reagent is nothing but benzene sulfonyl chloride is called Hinsberg reagent, C6H5SO2Cl. Remember that the primary and secondary amines are going to react with Hinsberg reagent and we get respective sulfonamides. Primary and secondary amines are going to react, I told you, and the product we get is a sulfonamide. Later I am going to write some examples for that one. So sulfonamides we are going to get, whereas tertiary amines does not react with the Hinsberg reagent. And this is the general test to identify or to distinguish between primary, secondary and tertiary amine. So the main function of Hinsberg's reagent is to distinguish primary, secondary and tertiary amine. So now we'll see how actually primary, secondary and tertiary amines are going to be distinguished if you consider one reagent, and that reagent is Hinsberg reagent, nothing but benzene sulfonyl chloride. So now let me write in simple manner how we can consider that. So in the first column I consider test, in the second column I consider observation, so what we observe, and in the third column I consider inference, the conclusion you can say. So as I said, this Hinsberg reagent is to distinguish primary, secondary and tertiary amine, and benzene sulfonyl chloride we know. So let me consider in general amine. So I am going to consider amine, and I don't know what kind of amine it is, whether it is primary or secondary or tertiary, and if you identify that particular amine, whether it is primary, secondary or tertiary, you need to react that amine with the Hinsberg reagent. Hinsberg's reagent, and that is nothing but benzene sulfonyl chloride, we know that. So if you consider amine and when it reacts with the Hinsberg reagent, and the first case, if you get a precipitate and which is soluble in alkali, see here, after mixing amines with the Hinsberg reagent, if you get a precipitate, okay, the precipitate we are going to get, and if you go on adding a particular amount of alkali, soluble bases are called alkali. Example, you can consider potassium hydroxide. So the precipitate what you get, and if you add a potassium hydroxide and alkali to that, and if that precipitate is soluble, and what I am going to say here is the given amine is nothing but a primary amine. So primary amines, they are going to react with the Hinsberg reagent and you will get a precipitate, and that precipitate is soluble in alkali. This is a condition for primary amine. if you consider a amine and react with Hinsberg reagent, if you get precipitate that is insoluble here, that is insoluble in alkali, that is insoluble in alkali, and what it indicates, that indicates the given amine is a secondary amine. Remember that the given amine is secondary amine because that is going to be react with Hinsberg reagent. Of course we get precipitate, but that precipitate is insoluble in alkali. If you go on adding potassium hydroxide, the precipitate remains as it is. The precipitate is not going to soluble in the alkali, and based on that I can say the given amine is a secondary amine. So when you consider amines and when you consider Hinsberg reagent and reaction, and if there is no PPT, if there is no formation of precipitate, okay, if you get as it is without any precipitate, and that indicates the given amine is what actually, that is the tertiary amine I am going to say. So this is how, by using one reagent, that is Hinsberg reagent, benzene sulfonyl chloride, and using that the given amine, whatever it may be, and we can identify whether it is primary, secondary or tertiary by reacting the given amine with the Hinsberg reagent. Remember, in case of primary amine we get precipitate, but that precipitate is soluble in alkali, whereas in case of secondary amine we get precipitate that is insoluble in alkali, whereas in case of tertiary amine there is no formation of precipitate in also. So this is how we distinguish primary and secondary and tertiary amine. Therefore the test which distinguish primary, secondary and tertiary amine is what actually Hinsberg reagent test. And we have a test for only primary amine. What is that? Carbylamine reaction, Carbylamine test. And this is how the reaction I can consider in simple, in general, how actually the physical observation and inference we are going to get here. So as I said, if you consider amines, okay, I am going to write it. If you consider amine, whether that is a primary or a secondary amine, when you react that with Hinsberg reagent, Hinsberg's reagent, and the product what we are going to get is sulfonamide, and that is actually the precipitate what we get, and whether that is soluble or insoluble in alkali, and based on that we classify that into primary or secondary, and if there is no precipitate, and the given amine is a tertiary amine. And now you need to know what is the reason behind that. This is the practical sense, how we identify practically primary, secondary and tertiary amine, and why actually in case of primary amine the precipitate is soluble in alkali, why in case of secondary amine the precipitate is insoluble, and why not formation of precipitate in case of tertiary amine. We will find out the reason for that one. So for that one I need to consider the reaction. So let us assume, first I am going to talk about when primary amine reacts with the Hinsberg reagent, and Hinsberg reagent we know that one, benzene sulfonyl chloride C6H5SO2Cl. Know that this is the structure of a C6H5SO2Cl, that is nothing but a benzene sulfonyl chloride Hinsberg reagent. This is the structure. So now, as I said, I am going to talk about the primary amine first. We will see what kind of precipitate and how it is soluble. So when you react with the primary amine, so one very simple primary amine I am going to consider, and I am going to consider primary amine as ethanamine. So C2H5NH2, that is nothing but ethanamine. Okay, and now when ethanamine reacts with what actually Hinsberg reagent, and what kind of a product we are going to get. So now for your simple reference I will write here, there is elimination of HCl. This is how HCl is going to be eliminated, and after elimination of HCl what kind of product we get, let me write over here. So this is the phenyl group, and we have S double bond O over here, and we have a nitrogen and a C2H5 and one hydrogen of here I am going to write here. So this is how when Hinsberg reagent reacts with the primary amine and we get this kind of compound, and this is actually nothing but sulfonamide. And now we will see what is the name of that one. So this is what actually the ethyl group. So the name of this compound will be N-ethyl sulfonamide. N-ethyl sulfonamide. So this particular group is nothing but sulfonamide group, and we have a ethyl group here. Therefore N-ethyl I have written, where N stands for that is alkyl group other than parent chain. So we have only one alkyl group, therefore N-ethyl sulfonamide I have written. So this is the sulfonamide what we get when Hinsberg reagent reacts with the primary amine. And now the question arises, due to the formation of this sulfonamide, the precipitate is going to be formed. And why this precipitate is soluble in alkali? I told you already, you can consider potassium hydroxide as alkali. Soluble bases are nothing but alkalis. So why the particular precipitate is going to be soluble in KOH or alkali? The reason behind that is, here we have a nitrogen and here we have a hydrogen over here, isn't it? And the hydrogen which is attached to nitrogen is acidic in nature. So try to know, this hydrogen is acidic in nature. Due to presence of acidic hydrogen on a nitrogen in a sulfonamide, therefore this precipitate is going to be soluble in alkali. And one more question arises, why this hydrogen is acidic in nature, isn't it? So since we have a sulfonyl group here, okay, so C6H5 SO2 sulfonyl group we have, that is electron withdrawing in nature, that withdraws the electron present on the nitrogen. So since there is a presence of electron withdrawing group, that is nothing but sulfonyl group, because of that reason the hydrogen which is directly attached to nitrogen is acidic in nature. Since hydrogen which is attached to nitrogen is acidic in nature, because of that the precipitate what is formed, that is going to be soluble in alkali, and based on that we can say the initial amine what I consider, that is a primary amine. This is the reason behind that. Okay, so why the amine, if you consider primary amine, when reacts with Hinsberg reagent we get a precipitate of that, since presence of acidic hydrogen due to presence of electron withdrawing the sulfonyl group, and the product is going to be soluble in alkali since there is a formation of hydrogen bond as we know. Now we'll see, if you consider secondary amine we get a precipitate. Okay, we get a precipitate, we get a sulfonamide, but that precipitate is insoluble in alkali. So now we'll see why the particular precipitate what we get, that is insoluble in alkali. Let me write a reaction for that. So now I need to consider the structure of benzene sulfonyl chloride. So S double bond O Cl I write here. So now I need to consider the one simple example for secondary amine. So I am going to consider this particular example for secondary amine. As we know, in the secondary amine, two hydrogens are replaced by alkyl group. Okay, so since two hydrogens are replaced, therefore this is an example for secondary amine. So when secondary amine reacts with benzene sulfonyl chloride or Hinsberg reagent, there is a remole of HCl in simple I told you, and the product what we are going to get here is, so let me write over here. So we have the phenyl group, yes, double bond O we have here, and now see it is going to be linked with the nitrogen, and on a nitrogen we have one ethyl group and one more ethyl group we have. So what would be the name of this compound? This is sulfonamide we know. Okay, so we have one ethyl and two ethyl. So therefore I am going to write here N diethyl diethyl sulfonamide. N diethyl sulfonamide, whereas N stands for the alkyl group other than the parent chain. So this is the alkyl group, one alkyl group, one more alkyl group, two ethyl we have, therefore N diethyl sulfonamide, that is the precipitate what we get. As I said, the Hinsberg reagent is going to react with the primary as well as secondary. When it reacts with secondary, we will get dialkyl sulfonamide in general you can say. So now this is a precipitate, but if you take this precipitate and you go on adding alkali, and this precipitate remains as it is, this precipitate won't dissolve in alkali. What is the reason behind that? The reason is, if you know the reason why the precipitate when primary amine reacts with the Hinsberg reagent is soluble, and the reason for that is acidic hydrogen, isn't it? But if you observe the structure of dialkyl sulfonamide, on the nitrogen we don't have any kind of hydrogen which is acidic. Apart from that, we have two alkyl groups. since there is the absence of acidic hydrogen on a nitrogen, because of that reason the sulfonamide or the precipitate what we get, that is going to be insoluble in alkali. In simple I can say absence of acidic hydrogen on a nitrogen. Because of that the secondary amine will remain insoluble in case of alkali. So now we'll talk about the tertiary amine. So now in case of tertiary amines I will consider the benzene sulfonyl chloride. When it reacts with the tertiary amine, where all the hydrogens are replaced by alkyl groups, alkyl or aryl groups. So all the hydrogens. So I have 3 ethyl groups over here, and when this reaction takes place. So now since on the nitrogen we don't have any kind of hydrogens, whereas in case of secondary amine we had 1 hydrogen, in case of primary amine we had 2 hydrogens. Since there is absence of a hydrogen, absence of replaceable hydrogen you can say on a nitrogen, therefore the tertiary amines does not react with the Hinsberg reagent. Reactivity of amines with Hinsberg reagent, minimum there should be presence of 1 hydrogen. In secondary we have 1 hydrogen, in case of primary we have 2, in case of tertiary we don't have the hydrogen atom on a nitrogen of tertiary amine. Because of that reason tertiary amine won't react with the Hinsberg reagent. If there is no reaction between these two, means there is no formation of precipitate. Okay, so since there is no formation of precipitate, and one can identify that the given amine is a tertiary amine. So this is how the primary, secondary and tertiary amines can be distinguished by using a well-known reagent is called Hinsberg reagent. The formula is C6H5SO2Cl. You need to remember the structure also. And in case of primary, precipitate that is soluble in alkali. In case of secondary amine, precipitate insoluble. In case of tertiary, there is no formation of precipitate. The reason behind that you should know. That is about how actually the amines are going to react with the aryl sulfonyl chloride. Sixth chemical property of amines: electrophilic substitution reactions. We'll move with that one. Electrophilic substitution. We know that aromatic compounds undergo electrophilic substitution reactions. Now we'll see, if you have electrophile, electron deficient species, how does there is substitution reaction in case of aryl group of aryl amines. We'll see that now. The reason behind that we'll see that now. For that one, let me consider one simple example of aryl amine, that is aniline. So phenyl group with NH2, benzene ring with NH2 is nothing but aniline, and we know that one on a nitrogen of aniline we have a lone pair of electrons. So this NH2 group is electron donating group. You try to know NH2 group is electron donating group. Since NH2 group is electron donating group, that is ortho and para directing. So this NH2 group is ortho para directing group, or I can say this NH2 group is going to activate the ring. Ring activation takes place when we have what actually electron donating group. This is in general, you need to remember, if we have electron donating group, that is ortho para directing. So what is the meaning of ortho para directing? Remember that I am going to talk about the electrophilic substitution reaction. So incoming electrophile is going to attach to the position either ortho or para, and the reason behind that is the group which is going to be attached with the benzene ring, that is electron donating group. Therefore this electron donating group helps us to know which position actually electrophile is going to be attached, and that is the reason for what actually you can call it as ring activators also. And why actually electron donating group is ortho para directing, we'll try to find out the reason for that one. As we know, in case of aniline there will be resonance structures. I explained this already, let me repeat that because it is very important to understand why ortho and para directing group this is. So on a nitrogen we have a lone pair of electron and we have what actually the phenyl ring over here, and this lone pair of electron is the main reason for the basic nature of this amine. So this lone pair of electron will shift in this fashion and the pi electrons will shift in this fashion, so we get a kind of a resonating structure. This is the arrow mark representation for that. So the second resonating structure I am going to write. So lone pair of electrons will shift here, therefore we get a double bond NH2 has been given, therefore nitrogen gets a positive charge. So pi electrons is going to shift here, therefore minus I am going to write here. So double bond we have here and here. So this negative will shift here and pi electrons will shift, and we get the third resonating structure, and let me write in this fashion. So double bond NH2 we have here as it is, so minus will come here since pi electrons will shift, and double bond we have here and we have here. So the next resonating structure I am going to write here. So the minus charge will shift here, pi electrons will shift in this corner, we get the fourth resonating structure NH2 plus we have here, so has been shifted here, minus I will write here, so double bond here and double bond here. Fifth and the last resonating structure is, so this will shift here, pi electrons will shift over that, so that we get NH2, the positive charge is neutralized by this, and we have what actually 3 double bonds. So 1 2 3 4 5 resonating structures we got. And if you observe the resonating structures, we came to know that we have what actually minus a sign. So what it indicates? That indicates that this particular center or this particular position is electron rich. Minus we have since electron rich. As we know, in general, if you consider this as the benzene ring, okay, and this is the substituent, in general you try to know, and this position is ortho position and this position is ortho position. This is a substituent. For example, if you consider NH2 in the place of X, the next carbon which is next to this particular functional group, so these two are the ortho. This is ortho, this is ortho, and exactly opposite, this is the para position, and one next to that, that is meta position, one next to that, that is meta position. This is how ortho, meta and para positions can be identified by knowing the substituent if you consider over here. Similarly, this position is ortho position, right? Whereas this position we have minus over here, therefore this is a para, and here also this is a para. So we have a ortho position, we have a para position. In these two cases, they are electron rich centers. So these are electron rich centers. So electron rich centers prefers the species with the lack of electrons, that is nothing but electrophile. So because of that reason, the incoming electrophile is going to attach either ortho position or para position. Sometimes ortho position, para position also, major and minor products we are going to get. So this is the reason if we have electron donating group. So electron donating groups are ortho para directing groups. Means electron donating group if you have, that directs the incoming electrophile to either ortho position or a para position. Why it directs to ortho and para only? Because of this reason, at ortho and para position, the position or that is a center with the electron rich. Because of that reason, the particular electron donating group directs the incoming electrophile to either ortho and para directing. That's the reason we call it as ring activators. And if you consider electron withdrawing group, that is exactly opposite, that is meta directing group, that is ring deactivating we can say. So right now we are going to talk about aniline, therefore NH2 group is electron donating and that is ortho para directing group. So if you know the ortho para directing group nature, now I can continue with the reactions of electrophilic substitution reactions. So this is the basic what I told about electrophilic substitution reaction. And if you get the word called electrophilic substitution reaction, and the well-known reactions are halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. We'll see one by one in how actually the aromatic amines, in particular aniline, is going to be considered in these electrophilic substitution reactions. The first one I am going to consider halogenation. In that I am going to consider bromination. So bromination, so how does electrophile is going to be considered in case of bromination, and how actually substitution reaction takes place. We know that electrophile, electron deficient species, so in bromination, as we know, the electrophile will be Br+. So now we'll see how actually the reaction takes place. So now I am going to consider aniline, benzene ring with NH2. Okay, so this is aniline. So when this aniline undergoes bromination reaction in the presence of bromine water, so bromine water we write in this fashion, Br2 bar H2, that is nothing but bromine water, and this has to be considered in case of room temperature when aniline reacts with the bromine water. So here I will write 3Br2. Okay, so Br2, 3Br2. So Br bond Br, from that heterolytic fission we are going to get electrophile, that we know. So bromine water, it is going to react with room temperature, and the kind of product what we are going to get here is, let me write that first. So we have a benzene ring over here, and of course NH2 group we have, and to this position we have 1 Br, and to this position we have one more, and to this position we have the third Br. So this is the product what we are going to get when aniline undergoes bromination at room temperature with the bromine water. This is the product what we are going to get. As we know, this position is ortho position, this position is also, and this is para position. We'll write the IUPAC name of that one, so that you need to number that. So this is the 1, because NH2 will be the main substituent 1, and you can consider clockwise also, anti-clockwise also, so that the next substituent will be considering with the least number. Therefore 1, 2, sorry, this is 2, this is 3, this is 4, and this is 5, and this is 6. If you go with anti-clockwise also, the same kind of numbering we are going to get. So at the second position, fourth position, and sixth position we have Br. Therefore the name of this compound is 2,4,6 tribromoaniline. 2,4,6 tribromoaniline, plus we are going to get what actually the 3HBr we are going to get as the byproduct. So try to know the product what we got here is a tri-substituted product. So 2,4,6. So we have Br in second position, fourth position, and sixth position. 2,4,6, 3 Br we have. Therefore tribromoaniline. That is the product what we get when you consider aniline at room temperature. When you react with the bromine water, we get a tri-substituted product, that is 2,4,6 tribromoaniline. And here if you observe the position of the electrophile, and we have at the ortho position, we have at the para position, and that indicates that the theory what I explained, why NH2 or electron donating group is ortho para directing. But here if you consider the product, we have a tri-substituted, and the question arises, do we get a product with only one Br or mono substituted product? The answer is yes, but the condition is different. And we can get the single substituted product, but here we got the 3 substituted product. What would be the reason for that one? So the reason is again the group which is attached. What is that? NH2 group. NH2 group is highly reactive in nature. Why that NH2 group is highly reactive in nature? Because that undergoes the resonance, and that is stabilized by resonance. Since it is highly reactive in nature, therefore we get a tri-substituted product. And if you want a mono-substituted or single substituted product, we have to decrease the reactivity of NH2, or we need to consider one more step before moving with the bromination. And what is that step, and how we are going to get the single substituted product, I am going to explain here. So let me consider aniline, right? So if you carry out the bromination, we get a tri-substituted product, 2,4,6 tribromoaniline. But my interest is I want a single substituted product, and for that I need to consider a well-known reaction, that is acylation reaction. I am going to write over here. This is acylation reaction. As we know, for acylation reaction, as we studied in case of a second chemical reaction, you can consider acid chloride, you can consider anhydride, in some cases you can consider ester also, and here I consider CH3COCl. This is acid chloride, in particular acetyl chloride it is. So acylation reaction has to be carried out in a basic medium. Pyridine is a base, and the function of this pyridine, we know it removes HCl, which is formed in acylation reaction. So remember, if you want a single substituted product, before moving with the bromination, you should carry out acylation reaction. And what happens in case of acylation? H and Cl is going to be eliminated. For your reference, I have just underlined that. So what we are going to get? We are going to get here, so here we have N, one hydrogen has been eliminated, so we have one more hydrogen, and here I write C double bond O and CH3 we are going to get. Do you remember what is the name of this particular compound? This is aniline, the starting product, and this particular compound is, so here we have two carbons, isn't it? And this is the phenyl group, so phenyl ethanamide. So phenyl ethanamide is the name, and a well-known name, one more name we have, that is acetanilide. So try to know this compound is actually acetanilide. Already we prepared this acetanilide compound in the second chemical reaction. The same I considered here. So now I just converted NH2 group into NHCOCH3, and this we call it as what is that? Acetanilide. So next what I consider, I will carry out a bromination here. So Br2 bromination in the presence of acetic acid CH3CHH or ethanoic acid. What happens then? So we get the product I am going to write over here after bromination of acetanilide. So we get the product in this fashion. Let me write that first. So NH C double bond O CH3, and to the para product we are going to get Br. What is the name of this compound? This is acetanilide, and this is para-bromo-acetanilide. And 1, 2, 3, 4, and you can consider from this also 1, 2, 3, 4, 4 bromo-acetanilide. You can consider that also. So para-bromo-acetanilide. So we got what actually? Para-bromo-acetanilide. So when you take out the hydrolysis, or you can consider H2O, or you can write H plus or OH minus. Out of these two you can consider anyone. In that case what happens? Again we are going to get a substituted product of aniline. Let me write over here. So here we will get what actually? NH2 aniline, and we have Br as it is. The name of this compound is para-bromo-aniline, or you can call it as 4-bromo-aniline also. So now what we actually did in this reaction is, aniline is the starting material and para-bromo-aniline is the final material, and we got actually single substituted product. So we have only one Br, whereas in case of previous one, that is also bromination, we got a tri-substituted product, 2,4,6 tri-bromo-aniline. What we did in this case is, we carried out what actually? Acetylation or acylation you can consider, and after that we carried out to bromination. So then we got the para substituted acetanilide, and after hydrolysis we are going to get a para-bromo-aniline. Remember that first you need to convert this NH2 group into this particular group, and then what happens? That this particular group is a para-directing, and therefore we are going to get a para-bromo-aniline. So if you want to try substituted product, you consider bromine water at room temperature, and if you want a mono substituted product, you need to carry out acetylation. After that what actually? The bromination. And now one question arises again here, and the question is, in aniline we got that is ortho-para directing both, and why if you convert acetanilide, and why we are going to get a para-bromo-aniline? What is the reason for that? The reason is the group what we converted. See here, this is the group what I consider here. So this is the same group what I converted in case of acetanilide. So what happens? As we know, on a nitrogen we have a lone pair of electrons. So these lone pair of electrons, in the previous case of aniline, on nitrogen we have lone pair of electrons, and that involve in a delocalization in the benzene ring as it is. we get 5 resonating structures. Because of that, NH2 group is highly reactive. Because of highly reactive nature, we get a tri-substituted product. In case of this particular reaction, this highly reactive nature is converted into this particular product. So in this case, what happens? The nitrogen which is present, the lone pair of electron which is present on nitrogen, they are not involved in the delocalization. Then what actually happened? So this lone pair of electron will shift here, and that is going to interact with oxygen. So this is a reversible reaction, and what we get? N double bond. So lone pair has been shifted here, so pi electron will be shifted here, so O minus we get and CH3. So what I am going to say here is the lone pair of electrons which are present on the nitrogen, they are not involved in a delocalization in benzene ring, they are going to interact with oxygen, so that the reactivity of this will become less. Because of that reason, we won't get a tri-substituted product, we will get only mono-substituted product, and this is a reason for that one. Whereas in this case, particular example, lone pair of electrons are involved in a delocalization. In this particular example, the lone pair of electrons are not involved in delocalization, they are going to interact with the oxygen. Therefore, this particular group, that is less effective, less active when compared to NH2. Therefore, we are going to get only single product, that is nothing but para-bromoaniline. Of course, we get ortho-bromoaniline also, but the major product is a para-bromoaniline, or you can say there will be a steric hindrance if you consider what actually the ortho-bromoaniline. This is how, if you want a tri-substituted product, you go for this one. If you want a mono-substituted product, you can go for this one. That is how the halogenation or bromination of aniline takes place. Second electrophilic substitution reaction is nitration. We'll talk about that. Nitration of aniline I am going to discuss now, and we know that one NO2 plus will be the electrophile in case of nitration. So now, if you consider aniline, and if you carry out direct nitration of aniline is not possible. Remember that. Direct nitration of aniline is not possible because the NH2 group what we have, that undergoes oxidation and we get NO2 and some other groups. So since there is easy oxidation of NH2 group, so direct nitration is not possible, and we can consider nitration in this manner. So now let me write the reaction of that. So aniline I consider over here, and when aniline NH2 reacts with the nitrating mixture is nothing but the mixture of a concentrated HNO3 and a concentrated H2SO4. Remember that the word what I used is nitrating mixture. Nitrating mixture is nothing but the mixture of a concentrated nitric acid and concentrated sulfuric acid is called nitrating mixture. That is the main reagent for nitration to be carried out, and this reaction has to be considered around 288 Kelvin temperature. And what kind of products we are going to write? So let me write over here. We are going to get aniline with para substituted product. So nitration, therefore para nitroaniline we get here, and we are going to get one more product. Let me write that, and that is aniline with meta substituted, that is meta nitroaniline, and one more we get, and that is of ortho substituted, and that is nothing but ortho nitroaniline. So this is the para substituted. For your reference I will write here, this is meta substituted and this is ortho substituted. So when you consider aniline and when you consider nitrating mixture at 288, nitration takes place, we get para nitroaniline, meta-nitroaniline and ortho-nitroaniline also. Let me tell you, practically this is of 51%. This is of 47%, meta will be of 47% and ortho will be of only 2%. So we get a para product, we get ortho product, along with that we get a meta product also. So if I write this reaction, anyway one question arises. What is that? As I told you already, this particular group is a electron donating group, that is nothing but ortho para directing. Then how come we got a meta substituted product? The question arises, isn't it? So I have a reason for this. Why actually the meta nitro aniline we are going to get, why we are going to get a meta substituted product, and the reason I am going to write using with an equation. So if you consider aniline, and when you carry out a nitration in the presence of strong acid, in presence of acidic medium, in general I will write H plus, acidic medium we have H plus ions. So here when aniline reacts with H plus ions, as we know this is basic in nature, it can easily abstract proton. So what we are going to get? We are going to get NH3 plus. Here we are going to get NH3 plus. Since basic in nature, it abstracts the proton, therefore NH3 plus we are going to get, and the name of this compound will be anilinium ion. Anilinium ion. Anilinium ion. So anilinium ion, so this particular group, that is plus NH3 group, this is a meta directing group. So when you consider anilinium ion and when we carry out what actually the HNO3 nitration, and what we are going to get is we are going to get a meta substituted product. So NH2 and NO2 we are going to get, and this is meta nitro aniline. So because of this reason, some amount of para and some amount of ortho we have, and because of this reason, in presence of strong acid we get anilinium ion, and from that we are going to get a meta substituted product. Therefore remember that when you have aniline and when you carry out a normal nitrating mixture or nitration in presence of acid, the major compound will be meta substituted, meta nitro aniline we are going to get. Remember that we are not expecting any para or ortho. In this case we are expecting what is that meta nitro aniline, because of anilinium ion which is formed by abstracting a proton from the acidic medium. So try to know about this one. Direct nitration is not possible, therefore nitrating mixture has to be considered. In presence of acid we are going to get a meta nitro aniline will be the major product, therefore this kind of possible major product is going to be formed. Now in case of bromination, we have seen first we did acetylation, later bromination. Similarly, if you are interested in preparation of para nitro aniline, see sometimes the question is how you convert aniline to para nitro aniline. As we know how we convert aniline to para bromaniline, we don't carry out bromination directly, because NH3 is highly active, therefore that we consider acylation or acetylation. Later we convert to bromination and we get respective para bromoaniline. So if you want to convert aniline to directly para nitroaniline, what we have to do? The same procedure has to be followed. First you need to consider what actually the acetylation reaction. So this is the aniline, what I am going to draw here. So aniline contains the lone pair of electrons. So aniline. And when this is carried out acylation and I consider CH3COCl, remember I told you can consider acid chloride or acid anhydride also, it is left to you, and in presence of pyridine as a base, and there is removal of H and Cl, and therefore we are going to get a kind of product, and that product is nothing but phenyl ethanamide. So NH I will write, so C double bond O CH3, this is phenyl acetanilide ethanamide, and commercially you can call it as acetanilide. When acetanilide is going to treat with the nitrating mixture, that is concentrated HNO3 and concentrated H2SO4, we get a para substituted product. Remember, in case of acetanilide, and if you carry out any electrophilic substitution reaction, we get a para substituted product only. So NH we have here, so C double bond O CH3. So here we are going to get what actually the NO2. So try to know in the nitration, as I told you, NO2 will be the electrophile. So NO2 we are going to attach here. So the name of this compound will be para nitro para-nitroaniline. Para-nitroaniline, and if you want this is para-nitroacetanilide. Sorry for that, this is not aniline, para-nitroacetanilide. And if you want to convert acetanilide to aniline back, you need to carry out what actually hydrolysis, OH minus, or in presence of acid you can consider, and hydrolysis you can consider in general, and we are going to get what actually NH2 and NO2, and the name of this compound is para-nitroaniline or 4-nitroaniline also we can call it as. So first we did with the acylation, and later we considered what actually nitration, and we got to para-nitroaniline. Remember, if you want to convert aniline to para-nitroaniline, this is the only reason. Remember that in case of bromination, see, for your reference let me write over here, so NH2, and if you want what actually para-bromoaniline, if the question is if you are interested in para-bromoaniline, and sometimes if you are interested in para-nitroaniline, and if the question is how you convert aniline to para-bromoaniline, to para-nitroaniline, and you cannot consider the bromination directly, and you cannot consider the nitrating mixture directly, that is H2SO4 and HNO3, because this kind of reaction won't take place. As we know, the NH2 group is highly active in nature. It gives a tri-substituted product in case of bromine water, and here we are going to get what actually the para-substituted product here. So this kind of reaction is not possible. In both cases, if you want a para-substituted product, you need to follow with the acylation first, and later you need to consider with the bromination in case of para-bromoaniline, and in case of nitration you need to consider in case of para-nitroaniline. This is how nitration is going to be considered if direct nitration is not possible, and meta-nitroaniline will be the major product if we carry out in case of strong acid, and this is how if you want to convert aniline to directly para-nitroaniline, this is a reaction has to be considered. That is about second electrophilic substitution reaction, that is nitration. Third electrophilic substitution reaction is sulfonation. We'll see about that. The third one I am going to talk about sulfonation of aniline. Aniline I consider first. When aniline reacts with the concentrated H2SO4, we know for sulfonation we need to consider concentrated H2SO4. When this is going to be reacted, and the kind of the substance what we get here is, we get NH3 HSO4. Here I write plus and here I write minus. NH2 basic in nature, since we have strong acid, there will be obstruction of proton, therefore NH3 plus and HSO4 minus we are going to get, and the name of this compound is anilinium hydrogen sulfate. Anilinium hydrogen sulfate. When this is going to be heated around 453 Kelvin to 473 Kelvin in presence of H2SO4 again, and we are going to get the required product, that is, this is aniline, and we are going to get what actually SO3H. So here this is a product what we get, and to the para position of NH2 we have SO3H, and here we need to name this. So we have two functional groups, one is NH2 and SO3H, and in between these two SO3H has to be preferred. Therefore to this SO3H the NH2 group will be at a para position, therefore the name of this compound will be para-amino benzene sulfonic acid. Para-amino benzene sulfonic acid, and this may exist as in one more fashion I am going to write. So this particular NH2 group is a reason for the basic nature of the compound, and SO3H group is the reason for acidic nature. So what happens, SO3H donates proton Proton is nothing but H plus we know, and that proton is accepted by what actually NH2. So after this what happens? There will be a dipolar structure. And what is that structure? So this SO3H has given, therefore SO3 minus I write here, and that proton is gained by NH. So NH3 and plus I write here. So we get positive, and here we get negative, and this is, we call it as a dipolar ion. So when a dipolar ion is formed, by one group is going to lose proton and one group is going to accept proton, and that kind of ion we call it as a Zwitter ion. We know this concept. So Zwitter ion or dipolar ion we are going to get here. So name of this compound is para-bromo-benzene sulfonic acid, since this group has to be preferred while naming according to IUPAC. This is how sulfonation reaction takes place. Now we'll see the next one, that is Friedel-Crafts alkylation and Friedel-Crafts acylation. Friedel-Crafts. In general, I call it as Friedel-Crafts reaction, and it has alkylation and it has alkylation, as we know. In case of Friedel-Crafts reaction, we may carry out alkylation reaction, as we know. In case of the same, we can carry out the acylation reaction also. Do you remember, in case of a Friedel-Crafts reaction, we use one species as a catalyst, and the catalyst is AlCl3 aluminum chloride, and this has a very good nature, that is nothing but this is a Lewis acid. So this is a Lewis acid because this has ability to gain the pair of electrons. This AlCl3 receives a pair of electron, because of that this particular AlC will be the Lewis acid, and that acts as a catalyst. So what happens when AlCl3, or I can say in general Friedel-Crafts reaction, if you consider, I am going to talk about aniline. So let me write over here, if you consider aniline structure, okay, this is aniline, and of course in case of Friedel-Crafts reaction, Lewis acid AlCl3 we consider. So there will be a reaction of this aniline with AlCl3. Why? Because on a nitrogen we have a lone pair of electron, and it is Lewis base, and AlCl3 it is a lack of the electrons. You can say this can easily gain the pair of electron which is donated by aniline. Therefore there is a reaction between these two, and the product what I am going to write over is, here I am going to write NH2 and AlCl3, and positive and negative I am going to get, and this is a kind of a salt we are going to get here. This group what we get here, this is going to deactivate the benzene ring. In simple I can say this is a deactivating group. Since it is a deactivating group, this deactivates the benzene ring, therefore further reaction is not carried out. So because of that reason, there will be no alkylation, there will be no acylation in case of a Friedel-Crafts reaction. In general, there is no Friedel-Crafts reaction also, because we have aniline and the Lewis acid AlCl3, there will be a reaction so that the particular salt is going to be formed that stops the reaction where it is. That is about the Friedel-Crafts reaction. That is all about electrophilic substitution reaction. We studied bromination, we studied nitration, we studied sulfonation, and we studied Friedel-Crafts acylation also. Altogether is nothing but the chemical reactions of amines. In the next section I am going to talk about one new class of amines, that is nothing but diazonium salts.